Close your eyes for a moment if you can, or simply soften your gaze. Let the noise of your day fall away, not by force, just by choice, just for now. There is something happening beneath your feet at this very second. Something that has been happening for billions of years, without pause, without rest, without anyone asking it to. A vast ocean of liquid iron churning in total darkness, 1,800 miles below the ground you walk on, is generating a force field around this entire planet. And that force field is the only reason you are alive. No atmosphere, no blue sky, no oceans, no birds, no trees, no quiet Sunday mornings. None of it exists without this one invisible thing working in the dark. That is not a metaphor, that is physics. Earth's magnetic field is the reason our planet did not end up like Mars, a cold, barren, radiation-scorched rock with almost no atmosphere left. Mars lost its magnetic field billions of years ago. The solar wind stripped everything away. What remains is silence. We kept ours, and it has been holding the line ever since. But here is what most people never stop to consider. This shield is not permanent. It is not fixed. It is not the same today as it was 3,000 years ago. In fact, right now, as you listen to this, Earth's magnetic field has lost roughly 30% of its strength compared to what it was 3 millennia ago. And it is still weakening. There is a region over the South Atlantic Ocean, stretching from South America across to Africa, where the field has thinned so dramatically that satellites passing through it regularly malfunction. Astronauts aboard the International Space Station receive measurably higher radiation doses when their orbit carries them through it. The magnetic North Pole is no longer where it was. It is racing towards Siberia at about 34 miles per year. In the 1990s, it was moving at roughly a third of that speed. Something is shifting. Something deep and slow and ancient. And the question that sits quietly underneath all of this is, what does that mean for us? Welcome to Sleepy Science Podcast. I'm glad you're here. If this kind of exploration, the kind that pulls you away from the noise and sets you down somewhere quieter and stranger and more honest, if that resonates with you, consider subscribing. It helps us keep making these. Now, let's go deeper. People have known. Earth behaves like a magnet for a long time, though not always with the right explanation attached. Chinese navigators were using lodestone compasses by at least the 11th century, and for hundreds of years afterward, sailors trusted a swinging needle without anyone quite knowing why it worked. The first person to argue, with real evidence, that the planet itself was the source was an English physician named William Gilbert. In 1600, he published a book called De Magnete, in which he carved a sphere of magnetite into a small model globe, called it a terrella, and used it to show that a compass needle placed near the little sphere behaved exactly like a compass needle placed anywhere on Earth. His conclusion, radical for the time, was that the entire planet was, in effect, one giant magnet. He was right about the effect. It would take another 3 centuries before anyone understood the mechanism producing it. That mechanism stayed hidden for so long, partly because nobody could see what the deep interior of the planet was actually made of. The breakthrough came indirectly, through earthquakes rather than magnetism. In 1936, a Danish seismologist named Inge Lehmann was studying how seismic waves from large earthquakes traveled through the planet and noticed something that didn't fit the existing model of a single molten core. Certain waves were bending and arriving at unexpected times, in a way that only made sense if there were a solid inner core nested inside the liquid outer core. Her analysis, published that year, gave scientists the 2-layer core structure that the modern geodynamo theory depends on. A liquid outer shell where the actual dynamo operates, wrapped around a solid inner ball that anchors it. To understand what is actually happening to Earth's magnetic field today, you have to go somewhere no human being has ever been, and likely never will. Peel back the ground beneath you, past the crust, past the upper mantle, past the lower mantle, down through nearly 1,800 miles of increasingly dense, increasingly pressurized rock. And then you arrive somewhere that does not feel like Earth at all. A liquid ocean of iron and nickel, under pressures so extreme that the numbers stop meaning anything in ordinary human terms, at temperatures approaching 9,000 degrees Fahrenheit, hotter than the surface of the sun. And it moves, not gently. These are currents, hundreds of miles wide, flowing at thousands of miles per hour, driven by the heat bleeding outward from the inner core and by the rotation of the planet itself. This is called the Geodynamo, and it is one of the most quietly extraordinary things in the known universe. Here is the basic principle. Moving electrical conductors generate magnetic fields. Liquid iron is an excellent electrical conductor. Earth rotates. The iron moves. The magnetic field is born. But the geodynamo is not a simple loop. It is a self-sustaining feedback system, where the magnetic field it creates actually influences the flow of the iron that creates it. The field shapes its own source. It is, in a very real sense, a planetary engine that builds and maintains itself. Sit with that for a second. There is no external battery. Nothing is winding this up from the outside. The engine has been running on its own momentum, fed by its own heat, since before there was an atmosphere worth breathing. The heat that drives all of this comes from two places working together. The first is leftover heat from the planet's formation, 4.5 billion years ago, when Earth was assembled out of colliding rocky debris, and the energy of those collisions never fully left. The second, and more important over the long run, is the slow crystallization of the inner core itself. Earth's inner core is solid iron, roughly the size of the Moon, sitting at the very center of the planet. It is growing, slowly, but growing, at a rate of about 1 millimeter per year, as the liquid outer core cools and iron atoms freeze onto the solid ball at the center. When iron freezes, it releases heat. It also releases lighter elements, sulfur, oxygen, silicon, that were dissolved in the liquid, but do not fit into the crystalline structure of the solid inner core. Those lighter elements rise because they are buoyant, the same way a bubble rises through water. That rising motion, combined with the planet's rotation and the Coriolis effect, twists the flow into organized, corkscrewing columns of convecting iron. Those columns are the actual machinery of the dynamo. Physicists call this thermochemical convection. And it is the reason the field has not simply faded out over 4.5 billion years, the way a normal magnet would. For decades, this entire picture existed mostly as equations, because the physics involved, magnetohydrodynamics, describing how electrically conducting fluids move and generate fields, is brutally difficult to solve directly. That changed in 1995, when geophysicists Gary Glatzmeyer and Paul Roberts ran one of the first full three-dimensional computer simulations of the geodynamo on a supercomputer. Their model did not just reproduce a stable field resembling Earth's, left running over a simulated 40,000 years. It also reversed on its own, spontaneously, without anyone programming a reversal into it. It was one of the first pieces of strong evidence that ordinary chaotic fluid dynamics inside the core, not some rare external trigger, is enough on its own to flip the field from time to time. Later simulations, run by other groups with finer resolution and more realistic material properties, have reproduced the same basic behavior, lending real weight to the idea that reversals are simply what this kind of turbulent, self-sustaining system does periodically, the way a dripping faucet settles into chaotic, unpredictable rhythms under the right conditions. From that engine, the magnetic field expands outward through the mantle, through the crust, through the atmosphere, and far out into space, forming what scientists call the magnetosphere. The magnetosphere is not a perfect sphere. Picture a windsock. The solar wind, that constant stream of charged particles flowing outward from the sun at roughly 1 million miles per hour, hits the magnetosphere on the day side, and compresses it down to somewhere around 6 to 10 times Earth's radius. On the night side, it drags the field out into a long tail, called the magnetotail, that stretches past the orbit of the Moon. This is not a static structure. It flexes and breathes and responds in real time to whatever the Sun is doing. The solar wind itself does not travel in a straight line outward from the Sun. Because the Sun rotates, the charged particles it emits trace out a long, curving spiral through the solar system, something physicists call the Parker spiral, after Eugene Parker, the astrophysicist who first predicted the existence of the solar wind in 1958, before any spacecraft had confirmed it existed. He was right. It took years for instruments to catch up to the theory. Where the solar wind first meets the magnetosphere, there is a standing shock wave called the bow shock, similar in principle to the wave that forms in front of a boat moving through water, except this one is made of plasma and sits roughly 90,000 kilometers in front of the planet. Past the bow shock is a turbulent region called the magnetosphere, and past that is the actual boundary of Earth's field, the magnetopause, where the pressure of Earth's magnetic field finally matches the pressure of the incoming solar wind and holds the line. When the Sun erupts in a solar flare or a coronal mass ejection, billions of tons of charged plasma slam into the magnetosphere at extraordinary speed. The field absorbs the impact, deflects the bulk of it, and channels some of the particles down along field lines toward the poles, where they collide with atoms of oxygen and nitrogen in the upper atmosphere and produce the Aurora Borealis, the Aurora Australis. The colors are not random. Oxygen atoms, when excited at higher altitudes, around 200 miles up, emit a deep red glow. Lower down, close to 60 miles, oxygen produces the more familiar green. Nitrogen contributes the blues and purples along the lower edges of a strong display. The northern and southern lights are, in a very literal sense, the visible evidence of our shield doing its job, atom by atom, in real time. Inside the magnetosphere, there are two donut-shaped zones of trapped radiation known as the Van Allen belts. Discovered in 1958 by instruments aboard Explorer 1, America's first successful satellite, launched barely 3 months after the Soviet Union's Sputnik 1. The physicist James Van Allen had built a small Geiger counter for the mission, expecting it to register a steady, low count of cosmic ray particles as the satellite passed through different altitudes. Instead, the counter kept reading 0, not low, 0. Van Allen and his team eventually realized the true reading was not an absence of radiation, but the opposite. There was so much radiation at certain altitudes that the detector had become saturated and shut down entirely. What looked like nothing was actually too much of something. That discovery mapped out what we now call the inner and outer Van Allen belts. The inner belt, dominated mostly by high-energy protons, sits roughly 400 to 6,000 miles above the surface. The outer belt, made mostly of energetic electrons, sits farther out, somewhere between 8,000 and 26,000 miles. Between them is a relatively empty gap called the slot region. Think of the belts as overflow tanks. Particles that breach the outer magnetosphere get caught here and held, bouncing back and forth along magnetic field lines between the two poles, sometimes for years, rather than reaching the surface. Without the Van Allen belts, the radiation environment closer to Earth would be dramatically more hostile, and human spaceflight in low orbit would look very different. In 1962, the United States detonated a 1.4 megaton nuclear device 250 miles above the Pacific Ocean, a test known as Starfish Prime, partly to study exactly this environment during the Cold War. The explosion injected so many high-energy electrons into the region that it created an entirely new artificial radiation belt, one that damaged or destroyed at least 6 satellites in the months that followed, including one of the first commercial communications satellites ever launched. It took years for that artificial belt to fully decay. It remains one of the clearest demonstrations of just how sensitive this region of near-Earth space actually is. This entire system, the geodynamo generating the field, the magnetosphere deflecting the solar wind, the Van Allen belts trapping residual radiation, is layered, redundant, and extraordinarily effective. It has been running, more or less continuously, for at least 3.5 billion years. And yet, right now, it is changing. The South Atlantic anomaly is not a new discovery. Scientists have been tracking it since the early days of satellite spaceflight. But it is growing. The region of weakened field is expanding and drifting westward, and recent data from the European Space Agency's Swarm satellite mission suggests it may be in the process of splitting into two distinct weak zones, one anchored closer to South America, the other stretching towards southern Africa. What is causing it? The answer lies back in that liquid iron ocean. The flow patterns inside the outer core are not uniform. There are regions where the flow creates magnetic field that points in the opposite direction from the dominant field, essentially pushing back against it from below. One such region, sometimes called a reversed flux patch, sits beneath the South Atlantic, roughly under the border of Africa and South America. The field at the surface in that area is the result of the dominant field, and the opposing patch partially cancelling each other out. The way two speakers playing slightly out of phase can produce a quieter, muddier sound than either one alone. This is not a malfunction. It is the geodynamo being the geodynamo. Complex, three-dimensional, never perfectly stable, but it does have real consequences. Satellites crossing the SAA are exposed to higher concentrations of energetic protons from the inner Van Allen belt, which dips much closer to Earth's surface in that specific region, down to around 200 kilometers instead of the usual altitude farther out. The European Space Agency has documented component failures and data corruption events in multiple spacecraft during SAA transits, and mission planners now routinely design shutdown or safe mode procedures specifically for the crossing. The Hubble Space Telescope, for instance, has historically paused certain observations while passing through the anomaly, because the elevated particle flux introduces noise into its instruments that would otherwise contaminate the data. The International Space Station's orbit carries it through the SAA on every pass. Crew members have reported seeing light flashes, caused by cosmic rays passing directly through their retinas, more frequently during those transits. Astronauts have described these flashes, going back to the Apollo missions, streaks and specks of light with no external source, visible even with eyes closed. This is not theoretical. This is operational reality, right now in 2026. Predicting the day-to-day behavior of near-Earth space, including how bad an SAA transit or a solar storm will actually be, is its own discipline called space weather forecasting. In the United States, that work is coordinated by NOAA's Space Weather Prediction Center in Boulder, Colorado, which monitors solar activity continuously and issues alerts to satellite operators, airlines, and power utilities much the way a meteorological service issues storm warnings. The agency uses a scale for geomagnetic storms, G1 through G5, with G5 reserved for extreme events on the scale of the Quebec blackout or the Carrington event. On the solar side, spacecraft like the Solar Dynamics Observatory and the joint NASA, ESA Solar and Heliospheric Observatory, SOHO, keep a constant watch on the sun's surface for the flares and eruptions that eventually reach us, giving forecasters anywhere from tens of minutes to a few days of warning depending on the type of event. The moving magnetic pole is equally concrete. For most of recorded history, the magnetic North Pole sat somewhere over northern Canada in the general vicinity of the Boothia Peninsula. British explorer James Clark Ross first located and measured it in June of 1831, driving a flag into the ice at a spot he calculated using a dick needle, an instrument that measures how steeply a compass needle tilts downward as it gets closer to the pole. Navigators, pilots, and hikers relied on magnetic compasses calibrated to that general position for well over a century. By the early 20th century, scientists began tracking its movements systematically, with the Canadian government conducting repeated magnetic surveys of the Arctic through much of the 1900s. For decades, the pole drifted slowly, a few miles a year, staying roughly within Canadian territory. Then, sometime around the 1990s, it accelerated. By the early 2000s, it was moving fast enough that the World Magnetic Model, the mathematical model used by GPS systems, smartphones, and aviation navigation worldwide, had to be updated ahead of its normal 5-year schedule. In 2019, an emergency update was issued because the pole had moved far faster than the existing model predicted, that navigation errors were pushing beyond acceptable limits in high-latitude regions, particularly across the Arctic Ocean. The pole is now moving at roughly 34 miles per year, headed towards Siberia, on a trajectory that has essentially abandoned the slow, wandering path it kept for most of the last 2 centuries. It is worth being precise about what is actually moving, because the terminology trips people up. The magnetic North Pole is not the same thing as the geographic North Pole, the fixed point where Earth's rotational axis meets the surface. It is also not quite the same as the geomagnetic pole, a related but separate concept used by scientists modeling the field as a simple, idealized dipole tilted at roughly 9.5 degrees from the rotational axis. The magnetic North Pole is the actual, physical spot where a compass needle points straight down into the ground. And because the real field is lumpy and irregular rather than a perfect dipole, that spot can wander independently of the tidier geomagnetic pole used in textbook diagrams. It is this real, physical pole, the one an actual compass would find, that has been sprinting towards Siberia. Researchers who study the pole's motion, including a team at the University of Leeds led by geophysicist Phil Livermore, have traced the acceleration back to a specific feature in the core. 2 competing patches of magnetic flux, one beneath northern Canada and one beneath Siberia, that have historically fought each other to a rough standstill and kept the pole anchored over Canadian territory for centuries. Around the turn of this century, the Siberian patch appears to have gained the upper hand, stretching and elongating in a way that effectively pulled the pole toward it, like a tug of war where one side suddenly gets more players. Whether that Siberian patch keeps winning, stabilizes, or eventually loses ground again is an open question that current data cannot yet answer with confidence. How do we know any of this has happened before? The rocks tell us. When lava erupts and cools, iron-bearing minerals inside it, mostly magnetite, align themselves with whatever direction Earth's magnetic field happens to be pointing at that exact moment. As the rock solidifies, that alignment locks in place permanently, like a compass needle frozen mid-swing. By reading these magnetic signatures from lava flows of different ages, geologists have reconstructed the history of the field going back hundreds of millions of years. The same principle, applied on a much larger scale, helped confirm one of the most important ideas in all of geology. Starting in the early 1960s, researchers surveying the ocean floor with magnetometers noticed something strange, long, symmetrical stripes of alternating magnetic polarity running parallel to the mid-ocean ridges, mirrored almost perfectly on either side. Fred Vine and Drummond Matthews, working at Cambridge, along with Lawrence Morley in Canada, working independently, proposed in 1963 that these stripes were a magnetic tape recorder. As new ocean floor formed at the ridge and spread outward in both directions, it recorded whatever polarity the field held at that moment, then carried that record away like a conveyor belt as newer rock kept forming behind it. It was one of the pieces of evidence that finally convinced the scientific community that continents actually drift, confirming plate tectonics as something closer to fact than hypothesis. Lava is not the only material that can freeze a magnetic snapshot in place. Archaeologists and geophysicists working in a field called archaeomagnetism use the same underlying principle on fired clay, pottery, kiln linings, hearths. When clay is heated past a certain threshold, called the Curie point, and then cools, the iron-bearing minerals inside it lock onto the magnetic field present at that moment, the same way lava does. Because so much ancient pottery can be independently dated through other archaeological methods, researchers have been able to build detailed regional records of how the field's direction and strength shifted over the last few thousand years, filling in gaps that the slower geological record cannot capture at that resolution. Some of the sharpest evidence for that 30% decline in field strength over the last 3 millennia comes directly from this kind of dated, fired clay, pulled from kiln sites across the Middle East and the Mediterranean. What that combined record from lava flows on land and magnetic striping on the seafloor eventually showed was striking. The poles have not just wandered, they have completely reversed. North has become south, south has become north, hundreds of times across Earth's history. The last full reversal, called the Brunhes-Matuyama reversal, happened approximately 780,000 years ago. Before that, reversals occurred on average every 200,000 to 30,000 years, though the timing is genuinely irregular, not clockwork at all. Some reversals are separated by only tens of thousands of years, others cluster more closely together. And at least once, during the mid-Cretaceous period, roughly 120 to 83 million years ago, the field simply stopped reversing altogether for close to 40 million years straight, a stretch geologists call the Cretaceous normal superchron. Nobody fully agrees on why that pause happened, though it may be tied to unusually stable heat flow out of the core during that era. By the rough average, we are overdue. Now, that phrase, overdue, tends to generate a specific kind of anxiety. So let's be precise about what a reversal actually involves, because the reality is far less dramatic than the word suggests. A magnetic reversal does not happen overnight. It does not happen in a year, or a decade, or a century. The process takes somewhere between 1,000 and 10,000 years to complete, based on the paleomagnetic record, with most estimates clustering closer to a few thousand years for the core transition itself. During that transition, the field does not simply switch off. It weakens, yes, sometimes significantly, becomes more complex, with multiple magnetic poles appearing at unusual latitudes simultaneously, sometimes 4 or 5 distinct poles scattered across the globe instead of the familiar 2. The clean dipole structure we rely on for compasses breaks down into something far more chaotic and multi-directional for the duration of the transition. But it does not disappear, and this matters enormously because the field is not our only protection. Our atmosphere, that roughly 60-mile deep column of gas above our heads, is an independent radiation shield in its own right. Scientists estimate its protective effect against cosmic radiation is equivalent to roughly 13 feet of concrete. Even during a full reversal, when the magnetic field is at its weakest and most disorganized, the atmosphere continues to absorb and scatter incoming radiation before it ever reaches the ground. Life on the surface remains protected even if satellites and astronauts above the atmosphere do not enjoy the same buffer. The geological record confirms this. There is no correlation between magnetic reversals and mass extinction events. Researchers comparing the timing of the 5 recognized mass extinctions against the paleomagnetic reversal record have found no meaningful overlap. The field has reversed hundreds of times over the past several 100 million years. Life has continued, diversified, and flourished through essentially all of them. There is also a category of event less severe than a full reversal, called a geomagnetic excursion. During an excursion, the field weakens and the poles shift dramatically, sometimes wandering tens of degrees away from their normal positions. But the reversal does not complete. The field recovers and returns to its original polarity. Excursions are roughly 10 times more common than full reversals, which means the field has likely gone through many more close calls than actual flips. The Lachamps excursion, which occurred about 41,000 years ago, is one of the most studied. Researchers, including a team led by Alan Cooper at the University of Adelaide, reconstructed the event in detail using an ancient Kauri tree preserved in a New Zealand bog, a tree that had lived through the entire excursion and locked its timeline into its growth rings via radiocarbon variations. The field dropped to perhaps 5% of its current strength at the height of the excursion, and appears to have tilted so far that the magnetic poles briefly sat near the equator rather than near the geographic poles. Increased radiation reached the surface. Cosmogenic isotopes like beryllium-10 and chlorine-36, produced when cosmic rays strike the atmosphere, spiked in ice cores from Greenland and Antarctica, as well as in sediment records from that same period. And yet, no mass extinction. Neanderthals were alive during the Lashams excursion, in the final stretch of their existence on the planet. Anatomically modern humans were alive and expanding across Europe and Asia. Cave paintings were being made across parts of what is now Indonesia and Europe within a similar broad window. The field recovered. Life continued. There have been others. The Mono Lake excursion, dated to around 34,000 years ago and first identified through sediment cores from Mono Lake in California. Though its exact global extent is still debated among researchers, the Blake event, roughly 120,000 years ago, identified in deep-sea sediment cores from the North Atlantic. Each one tells a similar story, a period of weakening and instability, followed by recovery, with no clear signature of catastrophe left behind in the fossil record. It is worth being honest, too, about the limits of what we know. Not every claim connected to the Lashams excursion has held up cleanly under further study. A widely reported 2021 analysis, led by Alan Cooper's team using that same New Zealand Kauri tree, proposed that the excursion's radiation spike might have contributed to the extinction of Australian megafauna and shifts in Neanderthal tool use around the same period. Other researchers pushed back quickly, pointing out that the timing between the field's weakest point and those biological and cultural changes does not line up as tightly as the original paper suggested, and that Neanderthal populations in Europe were already declining for reasons likely tied to climate and competition with modern humans well before Lashams peaked. The honest position, and the one most paleomagnetists currently hold, is that the excursion happened, is well documented in the isotope and sediment record, and does not have a clearly established causal link to any extinction event. Science working in public, revising a striking claim after further scrutiny, is not a weakness in the story. It is the story. Some species that navigate using the magnetic field would face genuine disorientation during a period of significant weakening, and it is worth naming which ones rather than gesturing vaguely at wildlife. European robins carry a light-sensitive protein called cryptochrome in their eyes, one that appears to let them literally see the magnetic field as a visual overlay. A faint pattern of light and shadow tied to field direction. A mechanism first proposed by biophysicist Klaus Schulten and later supported by behavioral experiments led by researchers including Henrik Moritzen. Loggerhead sea turtles imprint on the specific magnetic signature of the beach, where they hatch and use that signature decades later to find their way back to nest in the same stretch of coastline. Atlantic salmon appear to use a similar imprinting strategy to return to their home rivers. Monarch butterflies combine a magnetic sense with a sun compass during their multi-generational migration across North America. For all of these species, a period of significant field weakening or instability could scramble the accuracy of that internal compass. Some populations might struggle, drift off course, or take longer to find breeding grounds. Whether humans have any equivalent sense at all is a genuinely open and genuinely contested question. In 2019, a team at Caltech, led by geophysicist Joseph Kirschvink, placed volunteers in a shielded chamber, isolated from outside electromagnetic interference, and manipulated a controlled magnetic field around them while recording their brain activity with EEG. Certain rotations of the field produced a distinctive drop in alpha wave brain activity, a pattern normally associated with the brain processing a novel sensory input. even though every volunteer reported feeling nothing and had no conscious awareness that the field had changed at all. Kirschfink's group interpreted this as tentative evidence of a subconscious magnetic sense in humans, something registered by the brain but never rising to conscious perception. Other researchers in the field have called for independent replication before treating the result as settled, and as of now, that broader confirmation is still pending. If it holds up, it would not mean people can navigate by magnetism the way a sea turtle does. It would mean something quieter, that this invisible field may be brushing against human biology in ways we have not yet learned to notice. But these changes unfold over generations, not overnight. Evolution operates on exactly that timescale. The same way these species developed magnetic navigation in the first place over millions of years, they retain other tools to fall back on: the position of the sun, the pattern of stars, gradients in ocean chemistry and smell, memory of the physical landscape itself. The timescale of a reversal is, from an evolutionary perspective, generous, even if it would look chaotic and alarming compressed into a single human lifetime. The more immediate concern, on the timescale that actually matters to people alive today, is technological. A significantly weakened magnetic field means more energetic particles reaching low Earth orbit, and, to a lesser extent, the upper atmosphere. Satellites become more vulnerable to component damage and data corruption. The SAA effect, currently localized to one region, would expand and could eventually be joined by similar weak zones elsewhere. Radiation hardening standards for spacecraft would need to increase across the board. Power grids, already vulnerable to geomagnetic storms driven by solar activity, would face a more hostile baseline environment even without a full reversal underway. History already offers a preview of what solar-driven geomagnetic disturbance can do, independent of any change in Earth's own field. In September 1859, a massive solar storm, now called the Carrington event, after the British astronomer Richard Carrington, who observed the triggering solar flare, struck Earth's magnetosphere so hard that Aurora were reported as far south as the Caribbean, and telegraph operators across North America and Europe found their equipment sparking, shocking them, and in some documented cases igniting fires, even with the power disconnected, because the induced currents in the long telegraph wires were strong enough to run the system on their own. If a storm of that scale struck today, with a planet dependent on satellites, GPS, and interconnected power grids in a way it was not in 1859, the disruption would be measured in the hundreds of billions of dollars. According to estimates from insurance and engineering studies conducted over the past 2 decades. More recently, the 1989 geomagnetic storm collapsed the Hydro-Quebec power grid in roughly 90 seconds, leaving 6 million people without electricity for hours in the middle of a Canadian winter. In October and November of 2003, a series of powerful solar storms, known as the Halloween storms, damaged transformers in South Africa, disrupted satellite operations, and forced airlines to reroute polar flights to avoid radiation exposure to crew and passengers. Each of these events was a hard lesson that the aerospace and power industries have not forgotten. There is a nearer term, less dramatic version of this concern that airlines already deal with directly. Commercial flights routed over the poles, common on routes connecting North America and Asia, fly through regions where the magnetosphere offers noticeably thinner protection against cosmic radiation than routes closer to the equator. Airlines, including Delta and United, monitor space weather forecasts and will reroute polar flights further south during significant solar storms, both to protect passengers and crew from elevated radiation exposure and to avoid the high-frequency radio blackouts that geomagnetic disturbances can cause in the polar region, since those routes depend heavily on radio communication in areas with limited satellite coverage. Pilots and flight crew who regularly fly polar routes are classified as occupational radiation workers in several countries, with their cumulative exposure tracked over their careers, the same way it would be for someone working around medical imaging equipment. the preparation for a weaker field, and for solar storms generally, is happening. Quietly, methodically, without headlines. Space agencies are already working on it. The Swarm mission, a trio of European Space Agency satellites launched in 2013, has been continuously monitoring the field's strength and structure ever since, producing the most detailed maps of its behavior ever made. That data feeds directly into satellite design, navigation system calibration, and space weather forecasting, alongside a global network of ground-based magnetometer stations, coordinated through a collaboration called Intermagnet, that has been recording the field's fluctuations at fixed locations around the planet for decades. Power grid operators in high-latitude countries, particularly in Scandinavia and Canada, have been installing geomagnetically induced current mitigation systems for years. Essentially, circuit-level safeguards designed to absorb or redirect the unusual currents that a strong geomagnetic storm can push through long transmission lines. And the timeline gives us room, even setting the solar storm risk aside. Scientists estimate that if the current rate of field decay continued in a straight line, it would take several more centuries before reaching strength levels comparable to what the paleomagnetic record shows during an actual reversal. The field may stabilize on its own. It may be in the early stages of an excursion rather than a full reversal. It may be doing something without a clean precedent in the roughly 200-year history of systematic magnetic observation that humans have kept. One detail keeps a lot of geophysicists cautious about calling this a reversal in progress rather than something milder. Overall field strength and reversal likelihood do not move in lockstep the way casual coverage sometimes implies. The field has weakened before by comparable amounts without ever completing a reversal. There was a period, roughly 40,000 years ago, distinct from Lasham's, where field strength dropped substantially and then simply climbed back. Researchers modeling the statistics of the reversal record, including work published by geophysicist Catherine Constable, have found that a declining dipole strength raises the odds of an eventual reversal without making one inevitable on any particular timescale. It is closer to a rising probability than a countdown clock. That distinction rarely survives being compressed into a headline, but it matters enormously for how worried any of this should actually make you. It helps to put Earth's field in context by looking at what the rest of the solar system is doing, or not doing. Mars almost certainly had a strong magnetic field once, generated by its own internal dynamo, and lost it somewhere around 4 billion years ago when its smaller, faster cooling core solidified and the dynamo shut down. NASA's MAVEN mission, which has been orbiting Mars since 2014, has directly measured the solar wind-stripping ions out of the thin Martian atmosphere at a rate that, extrapolated backward over billions of years, would account for the loss of most of the planet's original air. Venus, despite being close to Earth in size and mass, has essentially no significant internal magnetic field of its own. The leading explanation involves Venus's extremely slow rotation. A single day on Venus lasts longer than its year, combined with the absence of plate tectonics, both of which appear to interfere with the kind of vigorous internal convection that a dynamo needs to sustain itself. Mercury, by contrast, does have a real, if weak, magnetic field. First detected by NASA's Mariner 10 spacecraft in 1974, and confirmed in more detail by the Messenger mission decades later. It is a small planet with a surprisingly large iron core relative to its size. That core is still generating a modest dynamo of its own. At the other end of the scale, Jupiter's magnetic field is the strongest of any planet in the solar system, roughly 20 0 stronger than Earth's at the cloud tops, generated not by molten iron, but by a deep layer of metallic hydrogen. Hydrogen compressed under such extreme pressure that it behaves like a liquid metal. Jupiter's field is powerful enough to accelerate particles from its moon, Io's volcanic eruptions, into a radiation environment so intense that it would be lethal to an unshielded astronaut within minutes. Set against that backdrop, Earth's field looks almost modest. And yet it happens to sit in exactly the range needed to hold a breathable atmosphere in place around a world with liquid water on its surface for billions of years, long enough for something as improbable as us to show up and start asking questions about it. That question, how common a magnetic field like ours actually is around other stars, has moved from pure speculation into an active area of exoplanet research over the past decade. A planet's magnetic field is extremely difficult to measure directly across interstellar distances, so astronomers have been searching for indirect signatures instead. Radio emission generated when a planet's field interacts with its star's wind, similar to the process that produces Jupiter's own intense radio output, or signs of an atmosphere surviving in a place where an unshielded planet's atmosphere should have been stripped away long ago. No confirmed detection of an exoplanet's magnetic field exists yet, but several candidate radio signals, including ones associated with the nearby planet Tau Boetis b, have kept the search active. It matters for a very practical reason. Among astrobiologists weighing which nearby worlds might be able to hold onto a stable, breathable atmosphere long enough for anything resembling life to take hold, a working internal dynamo has become one of the leading items on the checklist. What the swarm data has already shown, in the years since 2013, is that the field's behavior is more complex and more regional than older, simpler models suggested. The South Atlantic anomaly is not simply a uniform weak spot. It has internal structure, distinct lobes with slightly different behavior, and the flow patterns in the core that generate it are themselves shifting year to year. The story is still being actively written, revised as new data comes in rather than settled once and filed away. Swarm itself is not flying forever. The 3 satellites, each about the size of a small car, were designed for a mission life of roughly 4 years and have already flown well past that original target through a series of mission extensions. A common outcome for successful ESA and NASA spacecraft that keep functioning long after their planned end date. ESA has funding approved to keep the constellation operating into the early 2030s, and the agency has already begun early planning discussions for a successor mission that would carry more sensitive instruments and, potentially, additional satellites to improve the resolution of the core flow models that current data can only approximate. Ground-based monitoring is not going anywhere either, and in some ways it does something satellites cannot. A magnetometer sitting at a fixed location on the ground records a continuous, unbroken timeline at that one spot, sometimes for well over a century at the oldest observatories, like the one at Greenwich in London, which has kept magnetic records since the 1830s. Not long after Ross first planted his flag near the pole in the Arctic. Satellites, by contrast, sample the whole globe, but only pass over any given point periodically, and their instruments eventually degrade or the missions end. Combining the two, a dense, long-running ground network with a global sweep of orbiting satellites gives researchers something neither one could produce alone. A record with both the spatial coverage and the multi-decade depth needed to actually catch a slow-motion process like this changing in real time. None of this monitoring exists to predict some specific doomsday date, because the science genuinely does not support treating it that way. It exists because a civilization running on satellite navigation, orbiting infrastructure, and continent, spanning power grids benefits, in very ordinary and unglamorous engineering terms, from knowing what the shield above it is doing this year compared to last year. The payoff of that knowledge shows up in a slightly better radiation-hardened satellite component, a slightly more accurate aviation route around a polar storm, a transformer built with a slightly wider safety margin. Nothing about it needs the story to be dramatic, to be worth doing carefully. There is something worth sitting with in all of this. We're alive at the one moment in the 5 billion-year history of this planet, when a species on its surface has the instruments, the mathematics, and the collective scientific infrastructure to actually watch the magnetic field change in real time, rather than only reconstruct it after the fact, from cooled lava and ocean sediment. Every generation before ours looked up at the same sky, walked on the same ground, were protected by the same invisible force, and had no idea any of this was happening beneath them. The Romans, who watched auroras dip unusually far south during periods of ancient solar activity, had no framework for what they were seeing. Medieval chroniclers who recorded strange lights in the sky described omens, not particle physics. We know. We are watching. We are measuring continuously from orbit and from the ground, and comparing this decade's data against the last, building a record that our descendants will eventually be able to look back on the way we now look back at those old lava flows. That is not a small thing. Consider, for a moment, the strange loop this creates. The instruments doing the watching, the satellites, the ground magnetometers, the supercomputers running Glatzmeyer and Roberts' descendants of that 1995 simulation, all exist because of a technological civilization that the field itself made possible. An unshielded surface stripped of atmosphere the way Mars was stripped of most of its own does not build satellites. It does not build the kind of stable, temperate, breathable world where a species has the leisure and the resources to spend decades constructing spacecraft whose entire job is to look inward and downward at the very force protecting them. In a very real sense, the field spent 3.5 billion years quietly building the conditions for something that could eventually study it. That is either a coincidence worth noticing or it isn't, and reasonable people can sit on either side of that question. Either way, the fact remains, plain and unadorned, right now, tonight, while you are lying still and listening to this, 800 miles beneath you, an ocean of iron hotter than the surface of the sun is turning without asking permission, without needing your attention, holding a line it has held since before there was anyone around to notice. Before you go, I want to ask you something simple. Of everything we covered today, what surprised you most? Was it the fact that the field has already lost 30% of its strength over the last 3,000 years? The South Atlantic anomaly? Affecting real satellites and real astronauts right now? The idea that Neanderthals lived through a period when the field dropped to 5% of its current strength and nothing catastrophic happened? Or maybe it was learning that our atmosphere, not the magnetic field alone, is actually the stronger shield, and that life has survived hundreds of reversals without missing a beat. Drop your answer in the comments. I'm genuinely curious what lands differently for different people, and your perspective adds something to the conversation that I cannot provide alone. If this kind of story is what you come here for, the slow, honest, quietly astonishing kind, subscribe to Sleepy Science Podcast. Every subscriber tells us there is someone out there who wants this, and that keeps us making it. Thank you for spending this time here. The field is still holding, and so are you.